Picture this. It's 2 a.m., mid-Pacific. The nearest piece of land is literally 900 nautical miles away. The ocean is relentlessly pounding against the hull. And, well, there's absolutely no tow truck coming if something goes wrong. Welcome to this explainer where we're diving into the metal that survives the sea. We're going to strip away the complex machinery and look at the very atomic structure that keeps a ship afloat. Because out there in the dark, the survival of the vessel depends entirely on the materials it's built from.
Think about it. Every single component we've covered in this series, whether it's the massive crankshaft driving the engine, the high-pressure tubes inside the boiler, or the mooring lines holding a 100,000-ton ship to the dock, is only as trustworthy as the material science behind it. If you pick the wrong material, or if you fail to understand how the relentless seawater slowly eats away at the right one, eventually, a part that quote-unquote should have been fine simply isn't. Bottom line? If the metal fails, the ship fails.
Section 1. Material Survival. Defining the limits. So, how exactly does engineering material science define and measure the mechanical properties necessary to ensure a component actually survives a uniquely brutal marine environment? We're talking about a place filled with constant vibration, cyclic loading, and extreme temperature shifts.
Okay, let's dive into this with the absolute basics of strength. Tensile strength. This is a material's ability to withstand pulling loads without necking, which basically means visibly thinning out, and fracturing. It's the absolute limit a piece of metal can be stretched before it visibly snaps. When a ship is pitching and rolling in heavy seas, there are immense pulling forces exerted on its structural members. Tensile strength tells engineers exactly how much stress that steel can take before a catastrophic break.
But, strength isn't everything. A ship can't be completely rigid, or it would literally crack under the ocean's immense forces. And that brings us to ductility. This is the ability of a material to undergo a permanent change in shape without rupturing. You absolutely want a ship's materials to be able to bend, flex, and yield under extreme, unexpected loads, rather than just snapping cleanly. Ductility is what allows a metal to deform and absorb energy, giving you a warped part instead of a completely broken one.
Rounding out our property survival toolkit is toughness. This is essentially a combination of both strength and ductility. It's the ability of a metal to absorb energy or deform plastically before fracturing. This is particularly crucial in freezing marine environments, where certain metals can suddenly become super brittle. High toughness prevents a piece of steel from shattering like glass from a sudden impact, ensuring it bends instead of breaking when, say, a rogue wave hits.
Section 2. Testing to the limit, proving the material. Because of course, it's not enough to just hope the metal has these properties. Engineers need to quantify these limits, proving a material's worth long before a ship ever leaves the port. And that requires some rigorous testing.
Now, this brings up a really fascinating engineering dilemma. How do you know a part won't break without actually breaking it? You have to be absolutely certain of its limits, but obviously you can't exactly destroy the brand new propeller shaft you're planning to install on the ship tomorrow.
The answer lies in two fundamentally different approaches to maritime materials testing: destructive testing and non-destructive testing. With destructive testing, you deliberately sacrifice a test piece from the same batch of metal to learn the absolute truth about its limits. With non-destructive testing, on the other hand, you inspect the actual in-service hero part that's going to sea, looking for invisible flaws without causing any damage to it whatsoever.
And this brilliantly illustrates how we deliberately punish metals in destructive testing to find their ultimate breaking points. We use tensile testing to literally pull a sample apart until it fractures. We use impact testing like the Sharpie or IZOD tests, swinging a heavy hammer into a notched bar to measure toughness. We use creep testing to measure slow deformation under sustained loads at high heat over incredibly long periods. And we use fatigue testing to see exactly how many repeated, cyclical loads a material can survive before cracking, which is absolutely vital for parts dealing with constant engine vibration.
Then, once the batch is proven, we use non-destructive testing on the actual ship components. This acts a lot like sonar or medical X-rays, but for metal. Ultrasonic testing sends high-frequency sound pulses into a weld or a shaft and reads the reflections to find invisible internal voids. Radiography passes X-rays or gamma rays through a component onto a detector, revealing density differences. Both of these methods let an engineer essentially peek inside the solid steel without ever cutting it open. Moving right along, let's see how we actually manipulate the metal itself. Through heat treatments, engineers can literally alter steel's internal grain structure to dial in the perfect balance of survival properties. Normalizing refines the grain by air cooling the metal after heating. Annealing softens it and relieves internal stress by cooling it incredibly slowly in a furnace. And tempering involves reheating the metal slightly after a rapid quench, perfectly balancing its final hardness against its toughness for specific high-stress machinery.
Section 3. The invisible enemy, corrosion. Because mechanical stress is really only half the battle, we now have to pivot from those immense mechanical forces to the silent, invisible villain of the ocean, electrochemical corrosion. Seawater is a highly conductive electrolyte, and let me tell you, it never stops trying to eat the ship.
Now, what's really interesting about this slide is the galvanic series. When you put two different metals in seawater, you create an electrochemical cell, basically a giant battery. One metal becomes the cathode and the other becomes the anode. The noble, cathodic metals like bronze and titanium, they're protected and survive. The less noble, anodic metals like zinc, steel, and aluminum corrode preferentially. The further apart two metals sit on this chart, the faster the less noble one will be eaten away.
Let's test that logic with a quick, real-world ship scenario. If you bolt a highly noble bronze propeller directly to a standard steel tail shaft and submerge them both in seawater, which one is going to corrode faster than it normally would? Take a guess?
The answer is the steel. Because bronze sits far more noble on the galvanic series, it turns the steel shaft into an anode. The steel will actually sacrifice itself to protect the bronze, corroding significantly faster than if it were just sitting in the ocean by itself. So the crucial point is that this is precisely why dielectric isolation, which is physically separating dissimilar metals, matters so much in marine design.
Section 4. The sacrificial fall guy. But what if you can't separate the metals? I mean, the hull of a ship is massive, and it's surrounded by dissimilar metals in a giant salt bath. Well, this brings us to a frankly brilliant human engineering solution to the galvanic corrosion problem.
We call it cathodic protection. The genius here is accepting that you simply cannot stop electrochemical corrosion from happening in the ocean, but you can control what corrodes. By installing a designated fall guy, you redirect the corrosive forces onto a sacrificial component designed specifically to rot away, leaving your incredibly expensive hull and propeller completely untouched.
These fall guys are called sacrificial anodes, and they're usually made of highly anodic zinc or aluminum. They literally take the electrochemical hit for the hull. If you look at a ship in dry dock and see heavily depleted, corroded anodes bolted to the hull, that's actually a sign the system is working perfectly. It's not a defect. For larger ships, an impressed current system might use a powered electrical charge to do the exact same thing. Either way, depleted anodes must be inspected and replaced on a strict schedule, or the corrosion will immediately turn its attention back to the ship's steel.
Sometimes, though, the absolute best way to beat metal corrosion is to simply not use metal at all. We're increasingly seeing non-metallic materials stepping into highly specific roles. Glass-reinforced plastics, or GRP, are used for lightweight, entirely corrosion-immune tanks and pipework. And Teflon, or PTFE, provides incredibly low-friction, chemically inert seals and bearing liners where metal would simply degrade way too fast.
Section 5. Reading the warning signs. Understanding the microscopic material science is fascinating for sure, but it ultimately has to translate into macro-level operations. How does a chief engineer actually manage these materials and monitor their degradation on board a working vessel?
It all comes down to strict, unwavering monitoring. Hourly logbook parameters track pressures, temperatures, and RPMs. Highly controlled bunkering protocols ensure fuel loading doesn't result in catastrophic pollution. And weekly safety routines test emergency equipment. Because equipment that is never used is equipment nobody can trust in a real emergency. Regular testing is what converts a theoretical safety system into a genuinely reliable one that catches material degradation early.
And this leads us to a crucial operational rule of thumb. If a temperature gauge is slowly creeping upward over a few hours but it hasn't hit the alarm bell yet, should you act? Yes, absolutely. A steady trend within limits is often the earliest, most valuable warning you will ever get. Experienced engineers treat a creeping temperature as an immediate action item. They don't wait passively for an alarm to force a reactive emergency response when the material is already in the process of failing.
Because at the end of the day, the sea never stops trying to break the ship. It is a relentless, high-stakes chess match between marine engineering and the ocean itself. You now know the science of how the metal survives and how we test it, protect it, and monitor it. But the ultimate question for any marine engineer on watch remains: when the next piece of metal inevitably starts to degrade, will you have read the signs in time?